We are going to discuss topic 11.2, infinite series. We first have to define infinite series in terms of a sequence. So you consider a sequence AN. You can sum up all the terms in the sequence. We first sum up the first few terms in the sequence, which we call the partial sum. So let me write down an sequence of AN. A sequence of AN comprised of the first term, second term, third term, etc. Up to infinite term. Then you can sum up the first term in the sequence, and you call this S1. If you take the first two terms in the sequence, then you call this S2. Then you can sum up the first three terms in the sequence, then you call this S3. Therefore, you can actually construct a sequence of Sn that is defined as Sn equals to the sum of An from 1 up to n. So this is what we call a partial sum. Partial sum is just simply the the first n term in the sequence of An. So the partial sum itself forms another sequence which we denote as Sn, where Sn is formed from the terms in the sequence. So that is how we define the partial sums. Then the series is defined based on the partial sum. Okay, so we talk about the partial sum Sn in the limit when the numbers of terms in the partial sum goes to infinity. So the last term in the partial sum, that is, well, the last term is the term at infinity. So in this sense, the Sn that contain infinite terms, which is written as A1 plus A2 plus A3 plus up to infinite term, is called an infinite series. Infinite series. So there are two concepts here. First is the concept of the definition of the partial sum. So the partial sum is just the sum of the first n terms in the sequence. Then you look at this partial sum. For a partial sum which contain infinite terms, then the limit of the sequence of the partial sum, which is written as this, which represents the limit of the partial sum, which is by definition the sum of all the terms in the sequence, is called the series, and usually we represent it by S. So that is how you define the sequence of partial sum and the series. Okay. Now, in case the limit of the partial sum sequence, which is a series, converges to a number, then we say the series converges. So that is how we have to define the convergence of a series. If no such values of L exist, then we say the sequence of partial sums of the series does not converge, or we say the series diverges. Okay, so before I leave these slides, I just want to reiterate again the definition of the series. So series is just the infinite sum in the partial sum series, which is formed from Sn, where n is running from 1 to infinity. But each of the n here is the, so I think I better not to reiterate this. Let me refer to the definitions here to become more careful when I define the series. So given a sequence of numbers, an, the expression of the form is an infinite series. So that is how we define an infinite series. Then if the infinite series converges, then we say the series converges. If it's not, we say the series diverges. Okay, so there are many ways of representing an infinite series. Either you represent the infinite series as in this term, or in this form, or this form, or this form, or this form. So they are all referring to the infinite series. If you take only a finite terms in the infinite series, then this is called the nth partial sum. So these are all the definition that should be easily understood if you go through the explanations of the terminology in the series. In actual practice, what we do is that we give you an infinite series, and then the purpose, then you have to tell what is the convergence limit of the infinite series. So this is basically what is important in the topic of series. So this is an example of a partial sum formed by the sequence of an, which is expressed in terms of half raised to the power of n minus 1. So you can form the partial sum of this sequence. Say you take the first n terms in the sequence, and then you form the partial sum. Then you find that the partial sums can be represented by this, right? So this is the first term in the partial sum, second term in the partial sum, third term in the partial sum. So if you keep on adding all the terms in the partial sum, so this is a partial sum. If you keep on adding s1 plus s2 plus s3 plus s4 plus add to infinite, then add to infinite terms, then the contribution of the later terms in the series will become smaller and smaller. So even though you are add up to infinite terms, but the sum s will not sum to infinity. It will just sum to a finite value, such as the example that is shown in example given by the partial sums of this sequence. Okay, now once we have discussed roughly what is the definition of an infinite series, then we are now going to look at a very, very specific infinite series, which we call a geometric series. So as I mentioned, the geometric series is, sorry, not the general series, is written as the sum of all the terms in a sequence running from, say, the first term up to infinite term. Okay, so this could be usually written as a1 plus a2 plus a3 plus a4, etc. But if the sequence of an that is used to construct an infinite series is in the form of an is in the form of the constant a raised to the power r n minus 1 for n running from 1 to up to positive infinity, then this is called a geometric series. So the geometric series has the terms in the sequence with an equals to the constant a times another constant r raised to the power of n minus 1. So here a is a constant and r is also a constant. A here has a specific name which we call the first term, and r is called the ratio. So an geometric series is completely specified by the initial term a and the ratio r. So once you know what is the initial term and the constant r, then you can obtain the geometric series, which is expressed in terms of the sum of ar n power n minus 1, where n runs from 1 to infinity. So when you write out this summation, you get a plus a raised to power r, a power 2 up to a power r n minus 1. So this is the term in the infinite series corresponds to the first term. This corresponds to the second term. This AR2 corresponds to the third terms. Then this corresponds to the n terms. Okay, then you have this to continue to sum to other higher order terms as well. So with the infinite series defined as such, then you can easily ask a very simple questions. What is the limit of the geometric series given in the form of sum of r raised to n minus 1, where n running from 1 to infinity. Okay, so this is a very typical example of what is the limit of the series. So the first series we will encounter in this chapter is the geometric series. So in most of the later discussions, we will be dealing with how to calculate the limit of an series given the terms in the series. For the geometric series, you can actually answer the questions of the limit for the series quite easily. Okay, there is some slight mistakes in the notes here. This should be a power n instead of just a subscript n instead of just an. Okay, I'm going to fix this later. So for the case of the geometric series, it is understood that if the magnitude of the ratio is less than 1, then the infinite series of the geometric series actually converge to a values of a over 1 minus r. So that is the limit of the series, provided that the magnitude of the ratio r is less than 1. For all values of a. A could be positive, A could be negative, A could be larger than 1, less than 1. It could be any number for A, but the magnitude of R must not be larger than 1. Here you can actually prove the convergence of the geometric series quite easily. In order to prove the convergence of the geometric series, you just have to follow the argument that is mentioned here. So first of all, you write down the partial sum of the first n term in the geometric series. So you write down the first term, second term, third term, up to the k term in the geometric series. Then you multiply this whole thing by the ratio r, so that you write down these equations. From these equations, where you just multiply the equation above by a factor of r, right? So then a become ar become ar2, ar square become ar3, ar power n minus 1 become ar10. Sorry, I think these terms become ar power n. Now, once you have written down the term of Sn and R times Sn, then you can take the difference between the two equations. You take Sn minus R times Sn. Then you will find out that this term will be cancelled off by this term. This term will be cancelled off by this term. And then this term and all the other terms will also be cancelled off, except the first term in Sn and the last term in Rsn. So by taking the difference between these two, then what is left is the first term A in Sn and the last term of Arn in Rs. Then this is just equals to this. Therefore, Sn would then be expressed as A times 1 minus R divided by 1 over R. So this result is easily obtained from the difference between Sn and R times Sn. So now we have a limit of Sn, which is taken to be A times 1 minus Rn over one minus R. So now this is an sequence. Sn itself is an expression of a sequence in n. So we ask the questions, what is the limit of the sequence of Sn when n go to infinity? Since a and 1 minus r are just constant, so I can pull out the constant 1 minus r, then the rest will be appearing in 1 minus rn. And according to what we have discussed earlier on, the number 4 in theorem 5, it says the limit of anything raised to power n is 0 when n goes to infinity if the magnitude of x is less than 1. Therefore, we conclude that if the magnitude of r is less than 1, then r power n will go to 0 when r magnitude is less than 1. So that is the result that is guaranteed by item 4 in theorem 5. So by making use of this theorem, then we conclude that r power n will become 0 if the magnitude of r is less than 1. So by doing that, then we can be sure that the limit of the geometric series that is written as this is equal to a over 1 minus r with the condition that the magnitude of r is less than 1. Now this is a very simple but yet important result. You have to remember these results because we are going to make use of the results in the other parts of the calculation when we study the convergence of a series. But for the case where r is larger than 1, then it can be shown that the limit of the geometric series will be actually diverges. So the details are explained here, which I'm not going to go into detail. So up to this point, it is concluded that if you have a geometric series that is expressed as a form of summation of AR raised to the power of n minus 1, when n runs from 1 to infinity, this would converge to 1 to a over 1 minus r if r, the ratio magnitude is less than 1, and s infinity, and then this would diverges to infinity if the magnitude of r is larger than 1. So that concludes the convergence of the geometric series. Then you can easily answer these questions by looking at this infinite series. So this infinite series is a sum of all the terms of 1 over 9 plus 1 over 27, blah, blah, blah. So if you look at this series very carefully, each of the terms here can be actually expressed in the form of a geometric series. For example, the ratio, which is the values of the next term divided by the term before it, are all the same. I think I have to take off this one. This is an. So for example, if you take 21 over 27, which is the next term, divided by 1 over 9, then what you get is 1 over 27 times 9, which is 1 over 3. Right, so if you take the term 1 over 18(1) divided by 1 over 27, then this is 1 over 87 times 27, so which is also 1 over 3. So then you can show that this is a geometric series with a ratio r as 1/3. Then this is the first term in your geometric series, and the first term in the geometric series is usually expressed as ar power minus 1. For the first term n equals to 1, so for the first term n equals to 1, this is just the a term, right? So from here, it is understood that this is a geometric series with the first term a equals to 1 over 9, and with a ratio r, which is equal to 1 over 3. Now, once you have determined the first term and the ratio for the geometric series, then the sum of the geometric series can then just simply be expressed as a over 1 minus r. So here, a is the first term, 1 over 9, and then R is just a ratio of 1/3. That will give you the sum of the infinite series. So that is a very, very simple example of calculating the limit of the geometric series with a constant A and a constant of R, which is calculated from the procedure I just mentioned. You just look at the first term, A, then you look at the ratio of the two terms, then this ratio will give you the values of R. Once you know the values of A and R, then calculating the sum of the geometric series would just be quite a straightforward applications. So then you have another example. It looks like this is a very complicated example that appears as the forms of the sum of 5/4 power 0 minus 5 power this one. Then you just have to analyze this power series, this series, then try to figure out what is the A value and what is the ratio. Right? So here the A values is always referred to the first term in the series and is known to be just equals to 5. So here A is 5 and the ratio of R is just the ratio between any two adjacent terms. So you can take this divided by this, or you can take this divided by this. So anyway, you'll be able to obtain the ratio, which is just n minus sign 1/4. So by doing that, you would be able to calculate the infinite series, the sum of the infinite series for the geometric series will be just equals to 4. Okay, so so that is note that explains a little bit of how to calculate the infinite geometric series. That be reminded that no matter how complicated the expression of the geometric series is, the series is simply completely specified by R and A. In other words, if you know what R and A is for the geometry series, then you know almost everything about the geometric series, including the most importantly, the sum of S infinity. Sometimes we just write S, sometimes we just write S infinity to represent the sum of the geometric series. Okay, this is another example that is a bit complicated, but actually it's not very complicated. So you are given this example of 5.23 dot 5.23 dot, where the dot means the two decimal of 23 will keep on repeating forever. Then you are asked to express this 5.23 dot in the form of an exact fraction. You want to write this as a number of, say, A divided by B, where A and B are just two integers, so that you can represent the 5.23 dot exactly. So this appears like a complicated question, but actually it's not. It is just an geometric series in disguise. What you can do is just to look at this 5.23 and break it into two parts. That is 5.23 dot is broken as 5 plus the plus the 23 dot. The 23 dot parts can be seen as the sum of dot 23 plus dot 23 plus dot plus 0 but dot 0.00023. So for the next terms, it's just like 0.00000023. So for every additions of two decimal points of 00, then you have another 23 follow. So that is how the dot 23 can be understood. So in this sense, you can now write down this dot 23 dot parts in the forms of 123/100 multiplied with an geometric series. So you look at this, you will find that this is just nothing but just a factor of 0.3 multiplied with an geometric series. where the geometric series is just 1 plus dot 001, 1 plus dot 0001, etc. So in this case, this geometric series is represented by a curly bracket, by a bracket with 3 dots, is a geometric series with a constant a of 1 and a r that is equals to 0.01. So now you can actually obtain the sum of the geometric series as just equals to a over 1 minus r. So once you slot in the values of a and r, you'll be able to obtain the exact expressions that represents the square root dot dot, which is just a number of 23 over 100 times 100 over 99, where this 100 over 99 is just a sum in the geometric series that represents this part. So after all these excursions of mathematics, then you are now able to cast the number 5.23 dot dot as the factor of 23 multiplied with the geometric series. And the geometric series turns out to be sum that leads to 100 over 99. The 100 over 99 sum is obtained by slotting in the values of a and r into the equations for the geometric series. And in order to arrive at the correct expression of an exact ratio that represents 5.23 dot dot, you have to be smart to identify that the dot 23 could be expressed as an geometric series. So the geometric series appears in a disguised form, in example 4. Once you have identified those geometric series, then you can actually solve the problem quite straightforwardly. Okay, so up to this point, we have already shown a few examples of the geometric series and how to calculate the geometric series. The conclusions of the geometric series is actually quite simple. You look at the series and then you try to identify if the series is a geometric series or not. If you can recognize that it's a geometric series, then the rest of the calculation is actually quite straightforward. You just have to recognize what is the term A and what is the ratio of R. Once you have obtained the A and R, then you'll be able to get the sum of the geometric series. In example 5, we are looking at another type of infinite series, which is not geometric, which is called an telescopic series. So the telescopic series is shown to be a series that is converged into one. Now, how to see how the telescopic series converges is actually require a little bit of algebra, which is not very trivial. So what you have to do is that you look at this telescopic series. It made of two terms in the denominator. So what you do is that you have to express the terms into the sum of two terms like this. 1 over n times n plus 1 is broken down into the difference of 1 over n minus 1 over n plus 1. Now, once you have broken down this term in the infinite series into the difference between two terms, then you can try to open up the expressions in the summation term by term. Okay, for example, you set n equals to 1, then you obtain this term. And you set n equals to 2, you obtain a pair of this term. When you set n equals to 3, then you obtain this pair of term. Where each of these terms in the pair, one comes from 1 over n, the other one comes from 1 over n plus 1. Now, what you can observe here is the trend that all the terms that is next to each other in the neighborhood will cancel off itself. That is, the term here, minus 1 over 2, and the term that is next to it will get cancelled off because of the opposite sign. The term minus 1 over 3 will get cancelled off by the term that is next to it. Likewise, minus 1 over 4 will be cancelled off 1 over 4 on the next term. So all the pairs that is adjacent to each other will all get cancelled off by all the other terms that is next to it. except that the first term and the last term. So finally, you will get what is left is the term of 1 and the last term in the partial sum of Sk. So finally, you would be able to find out what is Sk, which is the partial sum of the first k term. So then what you do is you let k to infinity. When you let k go to infinity, that will represent the partial sum in S, where the k runs to infinity. So the calculations of the infinite series is just equals to the limit of the partial sum Sk, where k tends to infinity. And that is just equals to 1 because the partial sum of Sk is 1 over k plus 1. So when k goes to infinity, then this term will just drop to 0. This whole term will just drop to 0, but k goes to infinity. So what is left is just 1. So therefore, we have just arrived at another solution to another example, which is the telescopic example. Here, we shown you that using a kind of algebraic tricks to cancel off all the terms next to each other in the partial sum of Sk, then you can calculate the limit of this telescopic series, and it turns out to be just 1. Now, the moral of the stories of example 5 is that the calculations of the sum of this infinite series is not trivial. Okay, you have to be smart to break down the terms into all this expression before you can arrive at the correct answer. And you cannot use any formula for calculating the sum of this telescopic series. So there's no formula or general formula like theorems that can help you to calculate the sums of this infinite series. So let us look at another example, which is the example of an infinite series comprised of all the individual terms given by n squared. And obviously, the sum will go to infinity. So therefore, this kind of series is divergent. It is very obvious that this is divergent to me, but if you want to really prove the series of n squared is divergent, then you have to go through all these arguments. But I'm not going to go through this by yourself. It's enough to explain to you that in example 6, we are looking at an example of an series that is not divergent. So not all series would diverge, not all series would be converged. You have to really prove using some valid mathematical argument to say whether an infinite series converges or not. So the simplest way to tell whether an infinite series is converges or not is the case of an geometric series. It's always very easy to tell a geometric series whether it is converges or not. But for some other general series, it may not be so obvious, like in the case of the telescopic series. For the divergent series, it is quite obvious. It is divergent because the sum will just go to infinity when all the terms gets larger and larger. Okay, so that is the discussions of the infinite series. As a conclusion to this topic, we have sort of like defined what is an infinite series. And then we have illustrated to you that in most of the cases, we want to know whether an infinite series converges or diverges. And then we also talk about a very, very important specific example of infinite series, which is the geometric series. We also look at a few examples, such as the telescopic series, which is convergent, but the convergence of this is not to be proven using any theorem, but you have to use some insight, mathematical insight, before you arrive at the values of the series. Then we also give an example of series that is not convergent. So the next few topics we will be looking into more details of the tricks or the tools that will help us to answer the questions of whether an infinite series converges or diverges. Okay, so that's all for this video recording.